Hey, AP Statistics, welcome to Chapter 10. We're going to be doing more inference in this chapter. We're going to be focusing on comparing two populations or treatments. This is all the two sample and the two proportion stuff that you've been seeing over the last couple of units. So by the end of this section, you should be able to describe the shape, center, and variability or spread of the sampling distribution of p hat 1 minus p hat 2. Getting into this two stuff. Determine whether the conditions are met for doing inference about a difference between two proportions. Construct and interpret a confidence interval for a difference between two proportions. Calculate the standardized test statistic and p-value for a test about a difference between two proportions. And perform a significance test about the difference between two proportions. So a bunch of two proportion stuff in this section. So we're going to start with a little bit of an example to try and make clear what this two proportion business is about. So let's say we've got school 1 where 70% of students did their homework last night. And so we now have P sub 1. We're going to use subscript 1 to refer to the first population, school 1. And so school 2, P sub 2, 50% did their homework last night. And so it's two different populations with two different proportions. So the counselor at school 1 selects a simple random sample of 100 students and records the proportion that did their homework. So that's p hat sub 1. So a sample from school 1, a sample proportion. And then we're going to also do the same for school 2. School 2's counselor selects a simple random sample of a different size, 200 students, and records the proportion that did the homework. All right, so to summarize all of this into what ends up, it's going to end up being a lot of symbols, but it's, not too bad. You just put a bunch of subscripts on the ones we already know. So we have population 1, and we have the parameter, which was 70% for population 1. We have the statistic, which we don't know what the statistic was, but that's p hat 1. That was that sample of 100, sample size 100. And then we have population 2, which is this population where p2 is 50%. We know that, which again, we're going to hypothetical here. In reality, we usually wouldn't know that. We'll reverse that in a second. And then we have a p hat statistic, that of that sample of 200. So n2 would be 200. So we just got to keep all our p's and n's straight with all these 1s and 2s and hats and no hats and so on. All right, so putting that all together, we can look at just, we already kind of know this. This slide looks like a lot, but this is the shape, center, and spread, or shape, center, and variability of each of those p hat distributions. So we're kind of ignoring them, like looking at them in isolation, ignoring p hat 2. The sampling distribution of p hat 1 would be approximately normal as long as we meet our n times p and n times 1 minus p condition, which we know p1 is 70%, so we're good. We meet 70 and then 30, so those are both 10, so our shape is approximately normal. The center, mu sub p hat 1, would be at the population, and then they don't write the condition for this one, but we remember that that's the random condition, that it's unbiased. So as long as we're getting an unbiased sample, that counselor is getting an unbiased sample, that would be the average p hat we'll get. And then the standard deviation of our p hats would be the square root of p times 1 minus p over n. And so you plug that all in, get that. And that's as long as we are less than 10% of the population. So we do need to assume a fairly large school and an even larger one over here. So the rest of this is pretty much the same. Normal counts, normal for large counts, easily met here, 100 and 100. The average p hat would be centered there. The spread would be that. So we end up with these kind of two separate p hat sampling distributions we could think about with those shapes. So those are these separate sampling distributions, but what if we kind of put it together? What if we did a p hat 1 minus p hat 2? We focused on the differences. If we did the proportion at school 1 minus the proportion at school 2, what types of what types of values would we get for that? And so what we have here is a simulated sampling distribution of the differences in sample proportions. So they got a p hat at school 1, they subtracted p hat at school 2, and then they plotted those values. And so, for instance, you see that little red dot there. That's an example of a 0.25, and that was the difference between a p hat 1 and a p hat 2. So one set of samples gave a p hat of 72% and 47%. If you subtract those, you get 0.25. And so that is a difference in proportions of 25. And so we see a whole range of values. these all are all positive right now, but in theory, in some, and certainly in some cases, it's possible for the difference to be negative if P1 is less than P2. But remember, P hat 1 came from a population that had a higher proportion. 70% did their homework, and on average from that, I guess not average, but that's the true proportion. So that's why these numbers are tending to be positive, and we don't see any dip below 0. But it is possible that would happen. All right, so that's an example of one difference there. All right, and then the center we can see is at 0.2, which that's where it peaks. And so if you think about what we're really doing, p-hats, each p-hat that we get here, each of these we can treat as a random variable. P-hat is a random variable. When we go out and get our p-hat, it's going to be a number. And so we're doing the difference of two random variables, and so we can just subtract the two averages of what those would be, the average p-hat and average p-hat, which ends up being P1 minus P2. This was 70% minus 50% gives us 20%. So on average, we're going to get a 20% difference, or 0.2 difference. But sometimes the difference is higher, sometimes the difference is lower. But that's where it's going to be centered at, is the difference between those two population proportions, P1 minus P2. And then the spread. So when we subtract two random variables, hope you may recall that we add their variances. And so what we can do is we can kind of look back at those two distributions. If we add their variances, we get a formula like this. So this was if we did the standard deviation of p hat 1, it was this, like the square root of this, and then the standard deviation of p hat 2 is this. Well, if we square both of those, add them together, and then take the square root, like that Pythagorean theorem of statistics, we get this formula. So this big ugly formula is just adding the variances of those two random variables, p hat 1 and p hat 2. And that is on your formula sheet. So if we take a look at the back of your formula sheet, right down there in that second row, let's see if I can, that second row, we've got those values we were just talking about, P1 minus P2, and then that square root of P1 minus 1 minus P1, all this whole big, this guy over here. So that is on your formula sheet. So when that formula is applied, we do get this standard deviation. And so now we have a sampling distribution of a difference of p-hats. And so to summarize that, if we choose a simple random sample of size n1 from population 1 with proportion of success P1, and then same from sample size 2 from population 2, the sampling distribution will be approximately normal. So we can cover that, the shape. If both the individual sampling distributions of P hat 1 and P hat 2 are normal, then the difference will be normal. And so basically we have to check those conditions. So the differences in P hat 1 minus P hat 2 will be approximately normal if the large counts condition is met for both samples. So we have to do N1 P1 needs to be at least 10, N1 1 minus P1, N2 P2, N2 1 minus P2. So a lot of this stuff's the same, it just gets doubled for our two proportion stuff. And then the mean is going to be P1, P hat 1, or sorry, the mean of P hat 1 minus P hat 2 is going to be P1 minus P2. And they don't specify the condition, but as long as both are non-biased random samples. And then the standard deviation, we can use that standard deviation formula as long as the 10% condition is met for both samples. So the conditions are kind of the same, it's just you got to check them twice for each sample. But that's the good news about this chapter. Conditions are basically the same. All right, so example 1, your teacher brings 2 bags of colored goldfish crackers to class. Bag 1 has 25% red crackers, and bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher takes an SRS of 50 crackers from bag 1, and a separate simple random sample of 40 crackers from bag 2. Let P hat 1 minus P hat 2 be the difference in the sample proportions of red crackers. So what is the shape of the sampling distribution of P hat 1 minus P hat 2, and why? So the shape will be approximately normal. That's good. That's kind of the same, as long as N1 P1, so that was the first sample, 50 times its proportion, which was 25%, so 12.5. Just made it over 10. So that value, and then N1 times 1 minus P, so that's 37.5. N2 and P2, so our sample sample size was 40 and P2 was 35%, so 40 times 35% gives us 14, and 40 times 1 minus 35 gives us 26. All of those are at least 10, so twice as many conditions, but the same conditions. That's the shape. The next one asks us about the mean, the center, and so that'll just be, that one's kind of just P1 minus P2, 0.25 minus 0.35, so on average, negative 0.1. There will be a smaller proportion in the first sample, on average. And so the average of that sampling distribution is at negative 0.1 or negative 10%, 10% less. And then the last one, the spread. So because 50 is less than 10% of all, we know that there's more than 1,000 in the bag. And because 40 is less than 10% of all, we need to specify that we need to say both of those. Since each of these samples is less than 10%, we can use the standard deviation formula. And so this is P1, which is the 0.25, times 1 minus P1 over N1, plus P2 times N2, sorry, P2 times 1 minus P2 over N2, and then we take the square root, and that gives us the standard deviation of that difference of sample proportions. So this is a sampling distribution, just our sample is like a difference of sample proportions. So the difference, bag 1 minus bag 2, in the sample proportions of red goldfish crackers typically varies by about 0.097 from the true difference in proportions of 0.1. That is making sure we interpret that. So that is the typical distance that those differences are from the true difference of 10%. And so we expect some variability, almost 10% variability. So sometimes there will be a positive difference. We would expect that. All right, and that is sampling distributions for a difference of two proportions. In the next couple of videos, we'll get into actually calculating confidence intervals and significance tests, but this is the big idea that this is all based on.